Okay, good evening. Welcome to Astronomy on Tap. It's a very special Astronomy on Tap. This is our second anniversary. So thank you all for being here for the last 2 years. It's been really awesome to bring us the astronomy that we do in Santa Barbara and Galicia to you guys. It's also special because tonight is the eve of International Women's Day. So tonight is the first ever all-women Astronomy on Tap. I wanted to point out that last month was actually an all-male Astronomy on Tap, just because there's a lot of guys, but tonight you have some women. So I'm Charlotte, this is Dr. Sally Shaw, and we are your hosts for this evening.
Okay, so tonight I'm going to just give you an overview of what you've got in store. So we're going to start with a talk from Isabel all about how to take a photograph of an exoplanet. We're going to take a 5-minute break, and I want to encourage you all to text your questions for Isabel to the number right there, and also it's here. So make sure you text any questions you want to ask Isabel about her talk to that number within that time frame, and then we're going to bring her back to answer your questions. We're then going to go through recent astronomy in the news stories, so Charlotte and I will come back for that, and we'll give you another 5-minute break to go and get another drink if you so wish. And then we're going to finish with a talk from Monica, and that's about sort of what we put into space. And we'll then tell you any sort of the upcoming events we have, and there won't be another 5-minute break, so make sure if you have any questions for Monica on her talk that you text your questions during the talk or during the time that we're telling you about the upcoming events. And then we'll bring her back for the answer to the questions, and we'll finish with a raffle, which Charlotte will tell you about now.
Okay, so for the raffle this month, as usual, we'll be raffling our very sought-after Astronomy on Tap beer glasses. We also have some pretty awesome prizes to go with the raffle tonight, which are the Lego Women in NASA set. We told you about these a couple times. They actually sold out within 24 hours when they first became available. I got one for Christmas. It's really awesome. You should all want this. So make sure you stay to the end to be in for a chance of winning one of these Lego sets.
Okay, so just to encourage you to text your questions in, you can also, if we choose your question to ask to one of the speakers today, you will get a free poster. So these are posters that were designed by NASA to sort of, they're kind of like a vacation poster for exoplanets that have been discovered. And they're really nice. And you can also get 2 if you're a student, so extra bonus there. And if you don't want one of those, we also have some other NASA-themed items that you can choose from. So make sure you text in your questions.
Okay, all right, a little shameless plug. So everything we do here at Astronomy on Tap, we're all volunteers, but it does cost us money to put on these events. So we have to spend money on getting equipment and the prizes that you guys could win tonight. So if you feel willing and able to help us out, keep these events going, please put some few dollar bills in the tip jars that we're going to be passing around, just to help us keep going. I think Sally is going to model them now. And as usual, just to keep things a bit interesting, we're going to try and have a little competition between these tip jars. And we thought tonight, in honor of Monica's talk, we're going to be competing between Sputnik and Tesla. So, which one was more important to send into space? I don't know. Which one spawned more science? Well, who won? Only time will tell. But if you have a strong opinion about it, vote with those tip jars. Okay. And then I think Curtis somewhere. Someone should be bringing those around. He's not here. Come on, Curtis. So they'll be handed around during the evening. If you also want another way to support us and also get a cool shirt in the process, you can buy one of the Astronomy on Tap t-shirts, which are available at the front. And all of the proceeds from that will go to Astronomy on Tap. They're $10 each. Also at the front, there's loads of free magnets. And there's some Hubble Space Telescope postcards, which are pretty cool. So go and get some goodies at the front.
Okay, and finally, you'll notice that there are quite a few of us here tonight wearing flashing star pins, such as these that we are modeling right now. And we are all astronomers, physicists, and observatory engineers, and we can answer any questions you might have about anything at all related to astronomy tonight. So make sure you ask us questions during the break or afterwards.
Okay, so our first talk of the night is going to be given by Isabel Lipartito. She is a grad student at UCSB, and she spends most of her time doing research on developing new detectors, new cameras, to search for exoplanets and take really awesome images and data of those exoplanets, and that's what she's going to tell us about tonight. We also learned some new things about Isabel. I think she likes taking a lot of photos in general, not just of exoplanets, particularly of furrier things that are closer to home. Aww. Something else I found out about Isabel is that, like one of our previous speakers from last month, she's also done some karaoke. So I'm not going to encourage her to sing for us now, but maybe we need to do like Astronomy on Tap karaoke. No, let's not do that. Okay, so let's please welcome Isabel to the stage.
Thank you, Charlotte and Sally, for the wonderful introduction and reminding me of spring break 2015 at Montreal, because, that's where you go for spring break. It was warmer than where I was. So, hello, I'm Isabel Lipartito. I'm a third-year graduate student at the University of California, Santa Barbara. And photography may be what I do in my free time, but I want to tell you today about the sort of photography I'm trying to do for research. Specifically, how to take a picture of an extrasolar world. So I think it would be excellent if we started with some basic definitions. So we are one planet in a system of 8 that goes around a star that we call the sun. Now we refer to it as the sun, but really it's just one star of many inside a galaxy called the Milky Way galaxy. And an extrasolar system is essentially a system outside our own solar system that has a star, that has planets going around it, but exo meaning outside. It's not within our own solar system. And for example, I include a wonderful discovery we recently made of a very interesting extrasolar system. There is a star found to be harboring 7 temperate Earth-sized planets called TRAPPIST-1. And I include for you a very beautiful artistic depiction, not a photograph, but very nice to look at. And so this is kind of what we're talking about. So I think we're all pretty familiar with the solar system, right? We've got 8 planets going around the star, the sun. And of course, every so often they line up for a selfie like this, This is a contrived image. They're actual photographs of the planet. We are able to image our own planets, but someone has put them very nicely in a row for educational purposes. In reality, the situation's a little different. Each planet is actually further spaced than the last. This is not a size to scale diagram. From the Earth to the sun, it would take light, the fastest traveling particle in the universe, to take 8 minutes to get there. If you want to get to Neptune, it would take like 250 minutes. To kind of get a sense of the scale of the solar system, maybe you recall an installation that was done a few years ago where some astronomers and students decided to scale the solar system to the size of Santa Barbara. So the sun would be at the start of Modoc Road in Santa Barbara, but you'd have to travel all the way to Galita to find the last planet, Neptune. They situated it at Los Cumbres Observatory. So that's about 8 miles. Even trying to scale the solar system down, it's still massive. Moving out a little further, we know our solar system is just one of presumably many within our Milky Way galaxy. Now, we live in a very beautiful spiral galaxy. We're in one of the arms. But again, we cannot photograph our own galaxy. This is an artistic depiction. The diameter of the Milky Way galaxy is incredibly massive. If you wanted, you could stack 200 million solar systems end to end and span the entire galaxy. And so with this picture, another thing I want you to keep in mind today is when I talk about exoplanets we've discovered, those we've discovered are really confined into this little red light cone you can see in the diagram. We've really only mapped out that small part of our entire galaxy. And if you think about it, there's a large galaxy around us, there's millions upon billions of galaxies within the universe. We've only mapped out a very small possible space of exoplanets, though we've still found quite a lot. You can see in the diagram, we did find a new exoplanet very far away from us. Most of the ones I'm going to talk about today are between, say, 5 and 100 light years from us, but this new guy is 13,000 light years from us. So if you're interested in that, how we found it, ask me at the end of the talk. Okay, so I'm talking all about exoplanets, right? And maybe we're wondering, well, why do we care? You know, we've got a good setup here on Earth. Why do we need more? Well, for several reasons. You know, some are sort of fun, some are sort of scientific. One being that we cannot experience the evolution of our solar system in real time. It changes on a scale much slower than the human lifespan. So if we want to understand how it evolves, it makes sense for us to find extrasolar systems that might have formed earlier, that might have formed later, so we can essentially get snapshots of what they might what a solar system might look like at different stages of its life. That's how we can piece together our own history. Another is the real big name thing I'm sure we all think about every so often, you know, philosophically or otherwise. Can we find extrasolar life? Well, best way to do that is to look for habitable planets. And now I do hope that the extrasolar life we find is as friendly as the Pixar alien. I hope they have "We come in peace" as a motto. It could be War of the Worlds. That's just a risk we have to take as scientists. But I do hope for the cute alien, right? When we talk about extrasolar life, we have to remember not all planets are created equal. Not all are in what we call the habitable zone of a star. There's a certain range of distance from a star where you can be too close, like Mercury and Venus, too hot for liquid water to exist. You can be too far, too cold for liquid water. And we've deemed liquid water as necessary for life. It sustains us, so that's our parameter for now. Now, it's sort of the Goldilocks zone is the habitable zone. Can you have liquid water? And I'm sure as Southern Californians, we have a great sense of the habitable zone. It's exactly Southern California. You can choose to live in Canada, where the water might be a little bit frozen. You can thaw it. You can choose to live in Florida, as I did for a long time, which is a swampy, lawless nightmare. You know, you gotta bail the water out of your neighborhood, per se. There's too much water. But us humans have found a range of habitable zones within our own planet. Our whole planet is more or less habitable. Maybe not Florida. Okay, so exoplanets were really conceptualized as early as Newton. He mused on them. But it wasn't until the 1990s that we got direct confirmation that there are exoplanets. 1992, they found a few exoplanets going around a pulsar. Now, that is a sort of rapidly rotating stellar remnant. So it was like, you know, great guys, we found them around a stellar corpse. Let's keep going. So 1993, I'm born. And of course, the field really took off after that. I'll take credit. 95, we find exoplanets going around 51 Pegasi, a sun-like star. So, you know, things are really heating up, I would say. Over the next 10 years, 90s and early 2000s, the field grew. We got maybe about hundreds of exoplanets in that time. Now keep in mind, this wasn't exoplanet photography. This was all done using indirect detection. You don't get a photograph of an exoplanet. You just get scientific confirmation of its existence. Now, the method they used back then was what I affectionately refer to as the wobbly star method. Don't quote me on this, it's not scientific. But essentially what you're looking for is when you're focusing on a star, you want to see it kind of wobbling in its motion. That's the implication that there is a rather large exoplanet going around it, affecting it. We may recall the law of gravity. All objects exert a gravitational force on each other. Stars exert gravity on exoplanets, causing them to orbit the star. But exoplanets, if they're big enough, can also exert a noticeable effect on stars, sort of jerk them around. Not enough to really change their motion, but enough that we can perceive it. Sort of like an overgrown toddler running around its parent and yanking it every which way. So that takes us up to about 2009, when things really took off, quite literally. We launched the Kepler Space Telescope into space. It focused on an area of the sky about as big as 2 scoops of the Big Dipper, so a pretty significant area of sky. And it used another indirect method called the transit method, where you again look at stars, and this time you monitor stellar brightness. You want to see if the output of stellar brightness is going to decrease as a planet crosses in front of it. Sort of like this graph here. The brightness is decreasing a little bit as a planet transits. So you are limited to stars where the planet is crossing directly in front, but Kepler was very prolific. It found thousands of exoplanets. So now we're kind of up to today, right? As of last month, we have found about 3,700 exoplanets, but most of them have been indirectly detected. Only 90 have been directly imaged. Why so few? That's something interesting, right? Okay, so let's go on about direct imaging. What do I mean when I say direct imaging? So it's a little different from how your eyes work, or often how you're used to seeing pictures of planets in our solar system. When we image things with a camera or with our eyes, we're looking at reflected light from the sun or an artificial light source. So a lot of images you might recall of Jupiter or of Saturn are reflected light from our sun reflecting off them. When I do direct imaging at UCSB, I'm actually looking for the intrinsic brightness of a planet. Every planet has its own radiation source, but it's in a light that human eyes cannot detect, in the infrared. So when we want to make sense of the images we take of planets, we often artificially color them and sort of translate the infrared color into something that makes sense to us. So on your right, you have an image of Jupiter done from its infrared light, but it's being colorized, so it makes sense to us. But keep in mind, we cannot technically see this light with our eyes, only with special instruments. Let's talk about that a little more. Planets, mammals, including us, not just the kitty, all produce infrared light. Now, planets have a geothermal core, and that's where they radiate infrared from. And all mammals do as well. And so maybe you've put on infrared glasses and you've been able to see things even in the very dark. So it's great to take images of planets like this, and always great to get another cat picture. Image your cat in infrared, tag on Instagram. But we can do you one better. We can take that light and use a prism to break it up into what we call a spectrum. Now, I've included the cover art for Pink Floyd's Dark Side of the Moon, because I think, in addition to loving the music, we keep that cover in our heads as a really good example of what I mean by this, what I mean by making a spectrum. You can see light going through a prism and being broken up into a spectrum. Our eyes can only see the rainbow. We can only see visual. But keep in mind, there's infrared light, there's ultraviolet light. There is so much light that we can detect with special instruments. So once we have a spectrum, really, what can we do with it? And this is the money shot. This is how we're going to find habitable planets. A spectrum from a planet, whether one in our solar system or one outside our solar system, contains a fingerprint of the planet. It tells you about its composition, it tells you about its atmosphere. We want this. We want to know, can a planet harbor water? And so by studying the spectrum, we can look for sort of signatures, sort of fingerprints within the spectrum that indicate there might be water, there might be oxygen. I've included some spectrum here from our planets in our solar system. And you can see Earth is incredibly different from Venus at the top and Mars at the bottom. Venus and Mars have carbon dioxide in their spectrum, but no signs of habitable life like water or oxygen, whereas Earth does. Now, of course, as Earthlings, we know the Earth is habitable, but if you were an alien looking at our solar system, this is how you'd find out for yourself, without visiting Earth, that it has water and oxygen, that it is habitable. And so this is the real scientific goal of exoplanet imaging. We want the light. Okay, so how do you do it? You know, I've gotten you all psyched up about the incredible things exoplanet imaging can do, but how on earth do we do this? Well, I may be simplifying a bit, but you just need a camera and a telescope. Maybe a little bit fancier than your Kodak disposable, but you get the picture. Here's a good example of a telescope, though. You can use this one. You just got to get to Chile. Okay, so the catch of exoplanet imaging is that it's incredibly difficult. You know, you can probably think of it yourself. I've just told you that we want a dim little planet radiating in the infrared, and we want to somehow image it when it's orbiting a star. Stars, their job is to be bright. That's really all they do. They don't contribute to society. It's just bright. And so a really good analogy I want to bring up that a wise person told me was, it is that you are given the task to image a single firefly. And that firefly is going to be right next to a football stadium lit up for the big game. So you got stadium lights, and you just got that weak little firefly. And you got to do it. But the catch is, the stadium is in Utah, and you're in Florida, because you're always in Florida. So just keep that in mind for kind of a human thought of how difficult it is. And sorry to knock Florida so much. I'm from there, so I feel like I can do it. Okay, so we're able to do it, though. I'm going to show you real images that we've taken. Well, not my group, but other groups, and eventually my group, too. You literally block out the sun or whatever star you're looking at. And I feel we all have an intuition of this tool as humans. You know, let's say you're driving late at night in a national park, and a grizzly bear comes up to you with his flashlight, like, "Hey, where are you going, buddy?" And you know, you want to see who's talking to you, so you just put up your hand, block out the flashlight, and so you can see the bear's face. Well, we do just that with what is called a coronagraph. And I think this is sort of a fun illustration on how a coronagraph works. It's not literally what looks like a black circle on a popsicle stick. You know, we don't hire an undergrad to sort of stand in front of the telescope with the popsicle stick. It wouldn't be very fair, would it? Not the funnest job. But we do have that effectively, just a little more fancy optical equipment. But by literally blocking out the star, we can sort of see the exoplanets around it. It's so much better. And so when you see images of exoplanetary systems, you're usually going to see a big black circle, and that's where the coronagraph did its job. That's where the star is blocked out. And so I present to you, again, a false color image, because it is an infrared, of the system Fomalhaut and its planet Fomalhaut b. And it may be pretty hard to see from where you're sitting, but there's a zoom in, and there that tiny little speck with the white arrow next to it is the planet. So this is with the coronagraphic technology. It is incredibly difficult to see. You might mistake it for just some dust on your telescope, but we're able to do it. And now I've got a video of another exoplanetary system, HR 8799. This one's pretty popular. You might have heard about it. I think you can see 4 exoplanets going around a star. It's being blocked out with a coronagraph, just like Fomalhaut was. And this was made by Jason Wang at Caltech. And I think this is just an excellent example of what we're able to do now. We've effectively got a movie of extrasolar planets moving around their star, and I just think that's beautiful. This was taken over the course of several years, same shot, just several times. And over the course of the years, you can see the planets move. We're really getting a full image of the system. Okay, so now here's a bit of the bummer. The state of the art is we are limited to big, hot planets far away from their star, beyond the habitable zone. So that's a bit of a bummer right now. But let's talk about why this is true and how we can improve it. So one thing you can do to fix the problem that the planets are so dim, you need to build a bigger telescope. Now, a telescope is essentially a light-collecting bucket. You can think of it as that. And if you want to collect as much light as possible, you just need a bigger bucket. And to illustrate this, I include an image of the Andromeda Galaxy. Now, the top and bottom image are the same field of view, the same galaxy. I didn't zoom in on the bottom one. This is exactly the same. Just the bottom one, they were using a telescope with twice the diameter, so essentially twice as big a bucket. And look what a brighter, more defined image they got. So that is a real plug for building a bigger telescope. To fix the problem that it is incredibly difficult to image planets close to their host star, the reason why we're limited to outside the habitable zone is because of resolution. Now, all optical systems, your eyes, a telescope, have an inherent resolution, and that essentially is the ability to differentiate 2 light sources that are close together when you're incredibly far away from them. We've all experienced the issue of 2 distinct things blurring together when you're so far away. And to solve it, it coincidentally turns out a bigger telescope will help. Resolution of a telescope is tied to its diameter. With a bigger diameter mirror, you're gonna get better resolution, and you're gonna start being able to probe planets in the habitable zone that are just closer to their star. So we are working on this. I definitely talk the talk, but we're walking the walk as astronomers. We have plans to build the 30-meter telescope. It's gonna be 30 meters, hence the name. That's still in progress. It's a bit of a ways off. So, you know, until then, we're just gonna wait. My lab is playing video games all day. No, we've got another thing we can do to probe exoplanets. I promise you, we play video games only half the time. So right now, I want to do a plug for the Mazzini Lab. That's the lab I work in. Here is a group photo. And so I told you to probe habitable zone exoplanets, we could build a bigger telescope. But the loophole is, if you can't wait for the bigger telescope, improve the camera. That's your other tool. And now, here, so you can kind of see into our lab, you know, it's not top secret, you're allowed to look at this photo. We are surrounding, right in front, is one of our cameras. We essentially are a camera building lab, and I am so happy to talk about this. Ask me at the end of my talk, ask me in the questions. I can't go into great detail because I'm short on time on how it works, but essentially we use a new technology involving superconductors to build an incredibly high resolution camera. So on the left, I just have a quick picture of what one of these cameras, we call them detectors, look like. It's the little rainbow square, fits in the palm of your hand. It's mounted into a gold box. And we built these in our lab at UCSB. And essentially, once in a while, we load everything up. Now, it is not just this guy on its own. It comes with a whole entourage of electronics, because you want to connect to a computer, optical systems, few other things. We load it all up and we bring it to Palomar Observatory. That's the image on the right. And we essentially mount it into a little cage underneath the telescope and point the telescope at the sky. We're good to go. It's that easy. A little more in depth, but I think you get the picture. So just on my last slide, I want to just plug a bit more. Here again is our newest instrument. We just finished it. If you remember the photo of our whole lab, some people looked really tired. Those are the ones who've been working on the instrument. We're shipping it in a week. This one's actually going to a telescope in Hawaii. So, you know, kind of getting all over America, making our way. And then in just the last image, you can see on the right of the very happy man. He graduated shortly after. That's why he's so happy. I just want to answer the question I get all the time is, can your cameras take pictures of people? And yes, they can. If you emit any light whatsoever, we got you. We can take a picture of you. But we prefer exoplanets. That's where that's where the money comes in. All right, thank you. I'm happy to take questions after the break.
Thank you very much, Isabel. We're now going to take a 5-minute break, so please go get more drinks and order food, and we'll be back.
Okay, so we've received loads of questions for Isabel, so we're going to go through as many as we can in about 5 minutes. So, first of all, why do we look for planets with liquid water?
So, definitely it's a very human-centric way of thinking about it, right? You know, we like liquid water, so shouldn't every other form of extraterrestrial life? And to be quite honest, that is a field of research of astrobiologists. There's many people who study extremophile organisms that even here on Earth can get by in very extreme environments. And people do think about, could there be organisms that survive without life? So when we think of the habitable zone, it is quite a fighting community. There are people who reject that definition and say we shouldn't be so human-centered. So the answer is definitely we are considering it, and it's quite complicated, yeah.
Okay. So another question we've had is, what is the limit of how large a telescope one can build? Is bigger always better for resolution?
So just by mathematics, yes, you do want the biggest mirror possible. But then, of course, the engineers see your diagrams and are like, no. Tone it down. There have been many incidences where they had a very big idea for a mirror and it cracked halfway through, or they just couldn't build it. So there is a limit. I can't tell you the exact number, but I do know that when they're trying to build a big mirror, there are many engineering considerations as to material, as to exactly how to construct it. For example, there are liquid telescope mirrors that are sort of a revolving bowl of mercury, so it's not a solid mirror at all. And there are segmented mirrors, so you don't really rely on one piece of material to do the job. So it is quite an engineering question, yes.
So can you tell us the current estimate for the number of exoplanets in our galaxy?
So the number that I quoted earlier, about 37K, of course it is March, so that might have gone up a bit. That is really most of them are within our own galaxy. We're not really probing extragalactic planets yet, probably a handful. If you remember that light cone I showed you, they are within that little light cone, except for one that they found sort of at the center of our galaxy, 13,000 light years from us. And that was discovered just in a very lucky situation where it happened to beam light towards us, sort of a relativistic effect, some complicated physics there, but it definitely was not any of the traditional methods of detection. But yes, we are confined pretty much within our galaxy.
So in the video you showed of exoplanets orbiting a star, what was the other bright stuff around the planets? Was that gas or noise in the detector or something else entirely?
That was the aliens that I'm not allowed to tell you about. No, that's an excellent question. And that actually, I didn't really talk about it, but it is the other side of my group's research. Those images of, it was HR 8799, were made from a terrestrial telescope. So all that light from the star, from the exoplanets, had to come through our Earth's atmosphere, which creates those sort of wobbly blobs we were seeing. Atmospheric turbulence, and it really is a major field of study. In fact, when we deploy our own cameras, we have several machines to try to correct that, to sort of take out the wobbliness from having a planet with an atmosphere. It's the price we pay for being able to breathe, but that essentially was atmospheric effects.
Okay, so this is one that's just come in. What's the difference between the telescope you work on and then the big radio telescopes that we hear about?
The radio telescopes are made by people I don't like. No, they're great. So we mostly work on Palomar telescope, so Caltech's telescope, just right down the road from us. And we're also going to be using Japan's telescope. We're collaborating with the Japanese Subaru telescope. So we don't image in the radio at all. We currently are working in the optical, sometimes in the ultraviolet, infrared. Radio telescopes essentially are in the radio, and they're better suited to focusing on, I think right now, different astrophysical phenomena that would produce radio waves. But they're more fun to look at because they've got the little sundial effect. I like those.
Okay, so just to wrap up, we just received a question asking, what are the names of your cats and how old are they?
Okay, thank you. Excellent question. All right, so the black and white one with the combat boots is my own cat. Her name is Charm. She is 13. She got her degree from Stanford in 1998. No, she likes to sleep. The other two are, I'm going to do a plug because I love this place, the Santa Barbara Cat Cafe. I was there with my partner one day, and we saw the cats do the cutest thing. So we shared the photo with the entire world. At least one of those cats has been adopted, but the other one, you can go get her. Her name's Wilma. She's 3 years old. She likes long walks on the beach. I love her.
Okay, let's give Isabel another round of applause. Okay, so it's now time for Astronomy in the News.
Okay, so the first thing we wanted to tell you about is last time we spoke a lot about the Falcon Heavy launching the Tesla into space. Actually, on that note, I've been told that Sputnik is winning at the moment. I think I kind of agree with that. But if you really care about the Tesla, the tip jars are now at the back, or at the entrance when you come in. But yeah, so the Falcon Heavy rocket launched last month with the Tesla on board. But if you want to see some rocket launches in your backyard, you can literally do that. So actually, SpaceX launches a lot from Vandenberg Air Force Base. And this is a photo taken from a backyard in Goleta, taken by Griffin, who's one of the other Astronomy on Tap hosts of this launch that was earlier this month. He wanted to point out that this was taken on an iPhone. So it was pretty impressive to watch. And you could feel the vibrations of that rocket. If you haven't seen one of these, I'd really recommend trying to look for them. There's going to be another one launching at the end of the month from SpaceX. You can actually sign up for email alerts. at this website. If you're interested, they'll email you when there's a launch going to happen, and you can watch it from your backyard.
Okay, so something that happened in the last couple of weeks is that there was an update on what is known as the NASA twin study. So this was a study that NASA researchers have been doing on a set of twins. And back in 2016, one of the twins, his name was Scott Kelly, he spent 340 days on the International Space Station. And his twin brother Mark, stayed at home for that entire duration. So this allowed researchers a very unique opportunity to study the changes that happen to the human body and brain whilst you're in space. So they presented some more results the last week, and one of those key findings that they found was that actually Scott's telomeres, so these are the caps on the ends of our DNA strands, and these are known to shorten as we get older. But while Scott was in space for 340 days, they actually got longer, which is almost like he got younger. And this is kind of, this is fairly exciting in terms of researching how we might reverse the processes that happen as we age. But it did turn out that once he got back to Earth, they then shortened again by the same, they returned to their original state. So no one is recommending going into space as an anti-aging treatment just yet, but, watch this space. They also found that I think it was 93% of his genes that changed when he went into space returned to their original activities when he got back to Earth. So everything got back to normal. Apparently his brain the speed for him to solve problems did slow down a little bit, but NASA are not quite sure whether this was down to readapting to Earth's gravity or actually just the very busy schedule he had when he got back to Earth and had to do a load of interviews for newspapers and stuff. So this is kind of important because back in December, you might remember that President Trump said that he wanted to send, he wants NASA to send people back to the moon pretty quickly. And this has actually also induced a sort of flurry of research into spacesuits. So this was also in the news recently. NASA actually, it turns out, are still reusing sort of very, very old spacesuits. And these kind of traditional big, white, spacesuits that you see in pictures, we've been using the same ones for almost 40 years now. And apparently they smell like a locker room. So there's been a big push to try and develop something new. If we're going to start sending people to Mars and to the moon again, we're going to have to do some more research and get a better spacesuit. So there's some examples here of what NASA have been researching. The one on the left there is called the Z1 suit, and this you actually attach to the outside of a sort of a vehicle, and you can climb into it through the hatch at the back, so you don't need an airlock. And then Boeing are actually developing this blue suit in the middle, which is been called the Space Hoodie because you just pull up the hood and zip it up, and it's the lightest spacesuit ever developed. So this is all been a big push. This research is going on. The British media also picked up on this, and the Daily Mail decided to focus on this aspect of it, which is the toilets. So apparently it turns out that astronauts just wear leaky diapers whilst they're out in space. So this is kind of sounds very unpleasant. It makes it even worse that they're wearing the same spacesuits after, for 40 years because they just wear leaky diapers. But I think the message from here is that, they freely admit there's no suitable solution for an inbuilt toilet to these spacesuits for female astronauts, which, because of the theme of this week's Astronomy on Tap, this is kind of important. But I think the positive message is that back when they first developed these spacesuits and they developed a system for astronauts to go to the toilet, they did not have any female astronauts, whereas now they do. So now it's a problem, and they're actually starting to work on it. So we're really happy about that.
Okay, so this is a news story that I was pretty excited about, and I think Sally was as well. It ties into both of our research interests. So if you were at my Astronomy on Tap talk like 2 years ago now, I talked about my research, which is about discovering how the first stars and galaxies form in the universe. It turns out that's really hard because those first stars and galaxies are so far away from us now that they're really, really, really faint. So it's really hard to see them directly. So we have to look for other ways to try and figure out when the first stars and galaxies formed and how that happened. So one of the ways that we can do this is by looking at the effect that the first stars have on the hydrogen gas around them. And it turns out that we expect that the first stars will create a pretty strong signal in basically the temperature of the hydrogen gas in the early universe. So what I'm showing you here is a prediction for how the temperature of the hydrogen gas in the early universe evolves with time. And the really important thing is you see this big dip sort of in the middle of this graph. And that's due to the first stars turning on, cooling down the hydrogen gas, and that gas can then absorb light from the cosmic microwave background. So this is just a prediction. This is something that we expect happens, and astronomers have spent over 2 decades trying to look for this signal. And the important thing is we know sort of where to expect this signal will be, and we know at what wavelength or frequency to expect to see this signal. But the exact wavelength or frequency tells us when the first stars probably turned on. So when this dip happens is when those first stars turned on. The problem is the frequency that we expect it to happen is in about the sort of 50 to 100 megahertz range, which is basically exactly where your FM radios are. So every radio on Earth is emitting radio waves at this frequency, and we're trying to detect a signal from the very first stars in the universe, which is at about the same frequency. So this is a super hard thing to do. So to do this, radio astronomers have to go to some of the most remote locations on Earth. Actually, if any of you are interested, you like astronomy and you're also very adventurous, I think like a radio astronomer is the job for you. So the experiment I'm going to tell you about is in the Australian outback. So this is a picture of their detector, which is about the size of a ping pong table, a tennis table. This is an experiment called EDGES, which is in the Australian outback. It's about 1,000 miles from the nearest city, because you have to be somewhere that's really, really quiet, away from all of the interference from radio waves that we produce. They also have these radio experiments in the Himalayas, in the deserts in South Africa. So very remote locations that you have to be able to work in to detect these very, very faint signals. They're looking for signals that are more than tens of thousands of times fainter than the interference from all of the other radio waves out there in the universe. So very, very small signals. But this team, EDGES, recently published their results where they think they've been able, in this paper, they have made a detection of this dip in the temperature of this hydrogen gas. So just want to show you this sort of zoomed in again. So this is the frequency of those radio waves and the temperature difference that they're trying to measure. And these curved lines here will show you our predictions of how big we think this dip is going to be. So this is what we predicted before we made the measurement. But what the EDGES team actually discovered is this. So it's pretty different. Certainly, it's much, much deeper than anyone had predicted. And it's much deeper than people even thought was physically possible. We don't understand why this is so deep. Why it's basically telling us that the universe is much, much colder than we thought it could have possibly been. And we don't know why. So Sally will tell you in a minute one possible reason for that. But the researchers in the EDGES experiment, they were pretty shocked by that too. So they went about trying to check their measurements. They actually spent over 2 years really trying to check what they'd done. They built 2 separate detectors. They pointed them all over the sky, in different parts of the sky. They wrote 2 completely different sets of software packages to analyze their data completely from scratch. And these wiggly curves are all the different colors, are all those different tests that they did. and they got the same answer. So they're pretty convinced that what they got is this discovery that this very, very deep dip in the temperature of the early universe. And it's also telling us when these first stars turned on. So you can see when the dip starts to happen is about 180 million years after the Big Bang. So now we've really got to go about testing this, not just with this EDGES experiment, but all these other, there's a bunch of other radio telescopes that are coming online in the next few years to see if they can confirm this result. And it will certainly be a really exciting confirmation of this sort of tantalizing clues about the conditions of the early universe. And before Sally tells you about some reasons why it might be this cold, I just want to have a little rant about the title of this, the article in Nature about this. So Nature is this, one of the most prestigious science journals in the world. So they come up with this headline that says, astronomers detect light from the universe's first stars. But that's not what they did, okay? So they detected the absence of light, that's that dip, the absorption of light, and it was not from stars, it was from the hydrogen gas that was cooled by radiation from the first stars. So even Nature didn't get this right.
Okay, so basically, so I'm a dark matter physicist. We build an experiment that tries to detect dark matter particles, and it turns out that this result has some, if it's really there, if it's confirmed, it has some big implications for what we can say about the properties of dark matter. So dark matter is this stuff that's out in the universe that kind of, we can see it's there by its gravitational influence, but we haven't managed to detect it as a particle just yet. So if it has caused this cooling effect, what it actually means is that in the early universe, when there was lots of gas and dust that was kind of cooling down, dark matter particles were kind of bouncing into the gas particles and taking away some energy to try and to help to cool them down. And it kind of tells you something about how often dark matter particles would interact with gas particles, basically everyday particles. And this is exactly what we look for in our experiment. So this is kind of very important to us. And we, as a dark matter physicist, we're kind of used to people thinking that it's not a real thing. Just, we say it's there, but we're not really sure what it is yet. So we had it's kind of hard to read, but somebody here said dark matter doesn't exist at all. This always comes up. The other comment at the bottom here was somebody said, oh, it could be a set of cosmic horses pulling the universe apart, which doesn't make any sense at all, because dark matter actually has gravity, it pulls things towards it. But this kind of linked in with, if you were at Astronomy on Tap last summer when I gave my talk on dark matter detection, you might have heard us talk about unicorns. So this is your cosmic horse right here. And we kind of make this analogy between dark matter and unicorns just because we haven't seen it yet, but it doesn't mean it doesn't exist, and we'd like to think it does. And I actually showed this plot last year to show you that the way we describe our dark matter searches in particle physics experiments is by, we kind of search what we call the magical forest, and we can kind of rule out parts of that magical forest. And it's basically, we can rule out certain masses of dark matter particles. So as the unicorn gets fatter, the dark matter particle gets heavier. As the target increases on the unicorn, that's kind of the probability of the dark matter particle interacting with a sort of standard everyday particle that makes up us all, like a proton or a neutron. And we can rule parts of this out by the experiments that we run here on Earth. And this is a limit from one of the experiments I work on. And what's actually important about this is that if this signal from the early universe, this cooling of stuff, if that tells us something about dark matter, it's actually going to be right up in the top left corner of this plot, where we're still not sure. It doesn't disagree with our results, basically. There could be some unicorns hiding in that region that we haven't yet detected. So that's very interesting to us, because it means that we're actually kind of using the wrong technology, and we need to think very seriously about how we run our dark matter experiments. And we need to we need to look for skinnier unicorns. So We need to push down that way and think about different ways to look for dark matter. But,
Okay, so this is kind of a cool story for those of you that have your own telescopes. So this is an amateur astronomer in Argentina called Victor Buzo, who was testing out a new camera on his telescope. And he decided to test it out by taking some pictures of some nearby galaxies. So he focused on this one galaxy, was taking photos every 20 seconds, and then was looking at his photos and gradually realized that something in this picture was changing. And you can see here from this, these are the compilation of pictures that he took, that there's this little spot appearing in the bottom right where that green circle is. And he realized pretty quickly, wow, like I've discovered something happening in the universe. Maybe I should tell someone about it. Though there were some problems. He didn't speak English, and a lot of the astronomy databases online are all in English. So he called up a friend of his who spoke English and had some contacts with professional astronomers. So they found this website where you can upload details about a new discovery in the universe. But apparently that website is very difficult to use, and they were trying to make an account, and it took a while. So it took about 2 hours for them to make this account, and they eventually posted the details of what they discovered. And then professional astronomers were able to start taking more images of this event. And it's actually a supernova going off. So this is a star, a dying star exploding. And the thing that's really amazing about this is that they were able to get it, Victor has taken this image in real time. He has seen the death of this star. And this is something that we've never, ever seen before. And only by chance was he happened to be looking at this galaxy at that time when this star died. And we're able to learn an awful lot more about the evolution of stars from these types of images. So what was published last week was a study in Nature, the journal I told you about, which had stupid headlines. But he teamed up with some professional Argentinian astronomers to describe what happened to this star in its dying stages. He was able to share with them his images of this star, this video, and they could describe how it died. So someone over here is not very happy about this story. So apparently Yair is a little bit pissed. Because he also had contacted Victor Buzo to ask him to share his photos with him. And apparently he agreed, but then he changed his mind later on because he wanted to work with the Argentinian astronomers, not with Yair. But it turns out Yair's parents are from Argentina, so yeah, so sorry Yair, but he wrote a paper about it anyway, but just not with the original, like, the very first photos.
Okay, so back in 2016, you may have heard that we discovered that our nearest neighbor, the Proxima Centuri, which is the nearest star to the sun, had actually had an Earth-sized planet in its habitable zone, which was, very exciting for us. It kind of meant that maybe there could be life on a planet in the star closest to us, which even, sort of 4-point-something light years away, maybe we could have sent a probe there to go and have a look, see if there was really some life there. People were very excited about this. Well, unfortunately, we discovered just last week that, actually there's some bad news for any life on that planet, which is a massive solar flare. So unfortunately, if this big ejection of sort of radiation from the star would have meant that any life on that planet would have been fried, according to this headline, or scorched, according to this headline, or, we dashed hope, according to this headline. So this is kind of very unfortunate. We don't really know how often these flares happen in this star, so it could be that one day in the future we discover that there really was life on that planet and it really was wiped out just last week. So that's kind of... that would be fun to to know about in the future. Yeah, I think this headline just summed it up here. It's totally screwed.
And finally, we just wanted to give you guys a little heads up, kind of literally. So just so you know, there's a space station that is falling to Earth. It's a Chinese space station called Tiangong. It's Tiangong 1, which was the first Chinese space station. They've actually got 3 space stations in orbit right now. This was the first. It launched in 2011 and was in use until 2015. And its orbit has slowly been decaying closer and closer to Earth. That actually happens to all satellites due to some drag in the Earth's atmosphere. But usually engineers are able to fire thrusters in the telescopes to keep them level. Unfortunately, all contact was lost with this space station a couple of years ago. So now it's just going to do an uncontrolled re-entry into the Earth's atmosphere. So obviously, some of the media has been a little bit worried about this. These were just some images that I found. Maybe a little extreme, things to be concerned about. This one was my favorite. I think it's Kuala Lumpur, so I don't know if people in Malaysia are particularly worried about this. So I just wanted to give you guys a little bit of reassurance. So we've been, at least the Chinese Space Agency, have been aware about this problem for a very long time. They've contacted the United Nations. You're going to have to tell me. I wrote it down because it was too long. But there's a United Nations Office for Outer Space Affairs. So it would be great to have that on your business card, right? And they're now coordinating with the Interagency Space Debris Coordination Committee to make sure that this goes as smoothly as possible. So it's now been taken over by the European Space Agency, ESA, who are in control of keeping up to date on the fate of this satellite. So if you actually go onto ESA's website, they have loads and loads of stuff about it. They have blog posts, regular updates, and they've got lots of nice reassuring statements on their website. So this is one of the plots from their website. It's showing you they've been trying to predict exactly when it's going to enter our atmosphere. That's still pretty uncertain. So if you look, the y-axis is showing you the predicted day that it will re-enter the atmosphere, and on the x-axis, this is the date that we're making the prediction. So we're getting better and better. At the moment, the most recent prediction is that it's going to re-enter sort of the end of March to the beginning of April. So just keep an eye out. They've also been able to predict where it might re-enter, which is all of this green region. And Santa Barbara is in that region, just so you know. They also handily showed the population density here. But the chance of it landing in any one place is very, very low. And in fact, it will break up as it enters the Earth's atmosphere, so it's going to be in very, very small pieces. They think that some of them will land on the Earth, but so much of the Earth is actually water and uninhabited that they say that the probability of being hit by a piece of this space station is 10 million times smaller than your chances of being hit by lightning. And very reassuringly, that in the history of spaceflight, no casualties from falling space debris have ever been confirmed. So I think we're fine. But just keep an eye out. Just keep an eye out.
Okay, thank you everyone. We're going to take another 5-minute break now, so make sure to get another drink. Okay, listen up everyone. I'm now going to introduce to you Monica Turner. So Monica is Canadian. I kind of found that hard to tell myself as a British person, but apparently she's Canadian, and she did her PhD on the high redshift intergalactic medium. She was a postdoc at MIT for a couple of years before moving to Santa Barbara to work at the LCO as a data analyst. So she works on sort of satellites, and basically Monica in her spare time likes to bake, and she actually made a gingerbread model of the physics building at the University of Victoria, which was where she did her master's degree. And you can see here, now this is really nice, really detailed. And you'll notice that in the top right there's a little smiley face on the dome. And it turns out that really is there. There really is a smiley face on that dome. And that's Canada for you, apparently. So she also likes to do tobogganing in the snow, which is another very Canadian thing, apparently. So here is a picture of her doing that. But she's going to be talking to you about things that we put into space. So please give her a warm welcome and a big round of applause for Monica Turner.
Hi, everyone. So I started working at LCO less than a year ago, this past June, and I switched fields completely. I moved from working on the intergalactic medium to satellites. And so for my new job, I had to learn many new things. And I was really struck by how little I knew about a topic that's actually very prevalent in our lives. So in my talk today, I want to share with you all of the things that I learned this past year. So I'm going to start at the beginning, which was just over 60 years ago with the launch of Sputnik. So Sputnik was the first satellite, and it was launched by the USSR in 1957. And it was named Sputnik because it means companion in Russian, or satellite. And it was kind of an odd-looking object. So here it is next to a dude for comparison. So it was basically just a sphere, and inside the sphere was a radio and a battery, and it had these 4 antennae that were about 9 feet long, and they just transmitted the radio signals. So Sputnik itself didn't actually take any kind of data. It was just a big radio, and it was launched up to an altitude of 360 miles, and it orbited once every 100 minutes. And then eventually, it just fell back to Earth. But the speed at which it was orbiting and that it flew in the atmosphere gave the scientists enough data so that they could soon after launch the second satellite, which was called Sputnik 2. So Sputnik 2 was much more ambitious. It was much larger, and it would go to a much higher altitude. And you might know it for one reason, which is its payload, or its cargo, which is a dog. So you can see in there, maybe. Here's a better picture. There was a dog inside Sputnik 2 named Laika. Yeah, but it's actually a horrible story. Because soon after Sputnik was launched, the cooling mechanisms failed, and it became extremely hot inside, and Laika died within a couple of hours from overheating. This is horrible. So, okay, let's move on to the next topic. Don't want to think about that. So in a better change of events, the US was not far behind the USSR, and they launched their first satellite called the Explorer 1 just a couple of months after. It was a bit different in design. It was much smaller, sleeker, and it had a few scientific instruments on it that were measuring the temperature, the radiation that was located up in orbit. And there were a few really important women behind the Explorer 1. So one of them was named Mary Sherman Morgan, and she started off as a chemist, and she worked during World War II doing explosives. And later, she went to work at North American Aviation, where out of her hundreds of male scientist colleagues, she was chosen to lead the project to design rocket fuel. And they were successful. They invented the Hydene, which was the first rocket fuel that was able to propel the Explorer 1 into orbit. Furthermore, have any of you guys seen the movie Hidden Figures? Ooh, yeah, great movie. So much like in Hidden Figures, there were many women behind the orbital calculations that allowed Explorer 1 to be launched into space. So here is a photo of the group of mathematicians at JPL, the Jet Propulsion Laboratory, which is located in Pasadena. And they were the ones that did the calculations to launch Explorer 1. So if you want to know more, there's a couple of books that basically have the same name, but one is Rocket Girl and one is Rocket Girls, and they will tell you more about these great women. So I highly recommend them. All right. So let's fast forward a bit until now. We'll do so with this video. So this video is showing the satellites that were launched around the Earth between 1957 and today. You can see very quickly that the field exploded. The USSR, the US were all launching their satellites. Other countries got in. Many countries don't launch their own satellites, but they do have their own in space that were launched by their allies. So you can see as it keeps going, so actually the yellow dots are satellites, but the purple dots and the pink dots, I believe, are debris. So debris could be anything from rocket bodies, things that fall off of satellites. Basically, they're just space junk. And at some point, the debris start outnumbering the satellites. So that's the situation that we are in today. So you can see we're moving forward to 2016 and to 2018, and so there are many debris, but there are still a lot of satellites. There's about 4,000 satellites that are in orbit, and about only 1,500 of them, so less than half of them, are active. The rest of them are just sitting there. They're not working anymore, and we have no way of bringing them back down to Earth. All right, so I'll tell you first a bit about the satellites themselves, and then I'll move on to the debris. All right, so there's 5 main types of satellites. The first type are communication. So these are used for radio, for internet, for phones. And one major constellation, one famous constellation, is called the Iridium satellites. So these were launched in the 90s, and they're used for voice and data communication. And they're famous because their antennae are made out of the giant gold doors. So that's what, it looks like a solar panel, but that's actually its antenna. And it's the size of a door, and it reflects a lot of light, which means that you can actually see the Iridium satellites with your naked eye, which I'll demonstrate that to you later. Then next is navigation. You've probably all used GPS on your phones. So the GPS stands for Global Positioning System, so it's a constellation of 24 satellites, and they're arranged in a very special way so that no matter where you are on Earth, you can always see at least 4 of those satellites, and in that way it helps triangulate your position. Then a very broad group of satellites are called Earth observation satellites, so this is anything from Google Maps to spy satellites that take pictures of the Earth, weather satellites, and this specific example might look familiar to anyone from the area. For me, it gives me some PTSD because a couple of months ago during the Thomas Fire, I was compulsively refreshing the website that was showing this data. It's from the NASA GOES satellite, and it shows the hotspots that are measured using infrared cameras, which Isabel was talking about. And it was basically showing it was the most up-to-date way to see how the Thomas Fire was moving. The next 2 categories are not as, they don't make up that many satellites, but they're still important. Space station, so here's the International Space Station, which is staying where it is for now, luckily, unlike the Chinese one. And then another important category, astronomy, our favorite category. So yeah, observing from the Earth sucks because there's the atmosphere and clouds and weather, and it's horrible. So you really want to put your telescopes in space, like the Kepler telescope, which Isabel told us a lot about as well. And here's the proof that you can see the satellites just with your naked eye or with the Yair's camera. So this is a photo by Yair in Santa Barbara. So if you go out at night around sunrise or sunset, the sun is still close enough that it will reflect off of the parts of the satellite because they don't actually make their own light. You need to see the reflection of light. And then you can see them making streaks in the sky. So the two short streaks are probably Iridium satellites, while the long one is the International Space Station. So when you were looking at the video of the orbits, you may have noticed something. The orbits, there's a lot of satellites that are really close to the Earth, and then there aren't many, and then there's this kind of ring around the Earth. So why is that? I'll tell you a bit about the different orbits of satellites. But first I have to go into a little bit of physics. So here I'm showing a picture of a satellite orbiting around the Earth. And what makes satellites so difficult to launch is, of course, the force of gravity. When you launch the satellite up, the gravity's pulling it right back down. So that's represented by the red arrow in this picture. So to make your satellite go in a circle instead of getting pulled right back down to Earth, you have to give it a bit of a kick. And you have to kick it in the direction that's perpendicular to the force of gravity. So that's what the blue arrow is showing in this picture. And to make a circular orbit, you actually have to kick it in a very specific speed. And an important concept here is that actually the force of gravity, so the strength of the red arrow, depends on the distance to the Earth. The closer you are to Earth, the stronger the force of gravity. If you're further away from Earth, the force of gravity is weaker. So here the red arrow is much thinner, which means that the kick that you have to give it, the blue arrow, is much weaker as well. So satellites that are far from Earth actually will orbit much more slowly. All right, so keep that in mind. So satellite orbits are divided by their altitude, which means their distance from the surface of the Earth. And this also means they're divided by their speed, because remember, the closer they are to Earth, the faster they go. So starting from the bottom, our low Earth orbits, they go up to 1,200 miles. Most satellites are in this orbit, mostly because it's cheapest to send satellites here. Then there's this kind of middle area between 1,200 and 22,000 miles. It's called mid-Earth orbit, or MEO. And finally, there's a very special orbit. This is the blue dot. It's called geostationary at 22,000 miles. This altitude is very special because it's the exact height at which the speed of the satellite will match the speed of the rotation of the Earth. So this means that any satellite that you put in this orbit is going to be over the same point of the Earth during its entire orbit. Oh no, I hope this... Sorry, hold on one second. Technical difficulties. All right, we're in business. Okay, so this is a demonstration of this geocentric orbit. So remember, you might also notice that it was just a ring of satellites in this geocentric orbit. They weren't spread out everywhere. And this picture will show you why that is. So here is showing the Earth rotating, and you can see that a satellite, its orbit is along the equator of the Earth. And so you can imagine if the satellite goes along this blue line, it's going to be over the same point for its entire rotation. But if you rotate this blue line to another angle, you can see that it doesn't work. The satellite would go from the northern hemisphere to the southern hemisphere. So this geostationary position actually only works when satellites are right above the equator. So that's what makes that ring of orbits in the video. So there's a couple of issues with the geostationary belt. One is that it's very crowded. It's a very popular region because it's nice to have a satellite that doesn't change positions. There's over 400 satellites in the geostationary belt, and it's particularly crowded above the US and Asia, so there's not a lot of space there. But another problem with the geostationary belt is that there are actually some countries that are above the equator that you can't see from the equator, like Canada. So what about Canada? So like Isabel said, we're sort of not in the habitable zone, And I can tell you it is indeed a frozen wasteland all the time. But we want the comforts of modern life. We want to be able to use our satellite phones when our cars get stuck in the snow. So what do we do? So there's a special orbit for northern countries called the tundra orbit. And it's, instead of being a circle, it's an oval. So this is what a tundra orbit looks like. And remember before I said that when a satellite is close to the Earth, it goes faster, and when it's far away, it goes slower. So in this oval, the satellite will go slow when it's very far away and fast when it's very close. So you want to position it so that your country of interest, like Canada, is facing the orbit when it's at its slow point. So then the satellite will spend a lot of time there. Now you do need multiple satellites for this to work, and maybe this, sorry. Come on. Yes, okay, so maybe this video will show you, give you a better idea. So I don't know if you guys have ever used Sirius XM in your cars, but this actually is we also have that in Canada because of this satellite constellation. So this figure 8 shows what the path that the satellites take when they're in a tundra orbit. So when they're very far from Earth, it's actually at the very top, and they go very slowly there, and they can cover the northern parts. And then when they're close to Earth, they do this kind of big zoom around the big loop at the bottom. So if you have 3 satellites, you can actually cover the region full time. All right. So I told you I would tell you more about debris, so that's what I'll talk about now. There's a lot of debris. There's 22,000 pieces that are tracked by NASA. Those are all bigger than a softball. And I think there's actually 500,000 pieces of debris that are bigger than a marble that NASA can't track. So these are really important to track because they could, the smaller ones can damage your satellites. They can erode it, damage the equipment. The larger ones could cause catastrophic collisions. And actually there has been a satellite collision very recently. In 2009, an Iridium satellite collided with an old Russian satellite. They were traveling at 26,000 miles per hour, so they were in low Earth orbit. They were going very fast. And this collision created over 2,000 pieces of debris. We were actually very lucky that there wasn't more damage done, because once you start knocking things out of orbit and there's a lot of other satellites there, you could start hitting them and it could cascade into kind of a chain reaction. So yeah, we were lucky that this didn't go worse, but it tells us that we need to be really careful and we need to work on collision prevention. And that's exactly what we do at LCO. So this is a shameless plug. So at where I work, Las Cumbres Observatory, we're a network of telescopes at 8 different sites around the world. And we're actually in a very special position to look at geostationary satellites in particular, because as I said before, geostationary satellites stay over 1 point of the Earth. So you need a telescope at each point that you're observing the satellites. And so that's what we do. We observe the satellites and we measure their positions very accurately. And we send these positions to companies that are responsible for maneuvering the satellites and avoiding collisions. So that's what we do there. All right, so for the rest of my talk, I'll tell you a bit about the latest technology and the future of satellites. So one very new development is something called CubeSats. So these are very small satellites that are 4 inches across cubes. And they're sort of customizable. You can get them pretty cheaply, and you can attach your own radio, you can attach your own camera, and you can launch them. It costs about $100,000, and the price is going down to launch your own CubeSat. So this allows a lot of new people to enter the market, like scientists groups, education groups, a lot of companies, which is generally a good thing. However, they can maybe be used for not so great purposes. So you can see that I wrote that they can carry human remains. So there is this one company called Elysium, and what they do is they'll take the ashes of your loved ones and put it in a CubeSat, and for $3,000 they'll launch it into orbit. And if that's not enough for you, for $10,000, they'll launch the CubeSat to the moon. So I think we're in the era of launching not so useful things into space, like Teslas. So as you probably saw in the Astro News, last Astronomy on Tap, SpaceX launched the Falcon Heavy, which is pretty cool because that's the rocket ship that's going to take us to Mars one day. But they needed a payload, and so they chose to put a car. All right, fine. So we wanted to know where exactly is the Tesla going. So LCO's own Tim Lister used a tweet by Elon Musk and some other information to actually figure out where the Tesla is going. And we pointed our telescopes at what we thought were the coordinates, and we actually found it. So this white arrow is showing a little dot that shows the Tesla flying into space. There's actually a website that's dedicated to keeping track of where it is. It's called whereisroadster.com. It follows the trajectory of the Roadster. So apparently the intention was for it to kind of shuttle between the Earth and Mars as a test for future missions that would behave in a similar way, but they overshot the orbit a little bit. So now it's a little bit crazy, a little bit unpredictable. So some astronomers are on the case. They wrote this paper, The Random Walk of Cars and Their Collision Probability with Planets. And they just wanted to see where the Roadster was going to go. And they determined that the probability of a collision with Earth in the next million years is 6%, which is actually a good thing because this greatly increases my chances of obtaining a Tesla Roadster. But all jokes aside, we know that by that time we're all going to be on Mars. So that's all I have to say about satellites and things we launch into space. Thank you very much.
Okay. Oh, thank you. Okay, thank you, Monica. So please keep continuing to text your questions to the number over there. You should come back in a minute, Monica, wherever you've gone. So we're going to take questions in a minute for Monica, but first we're just going to tell you about what we have coming up in terms of events for Astronomy on Tap over the next few months. So this is the number to text your questions for Monica on her talk to. So first of all, I want to tell you about the LCO Open House event. So this is Wednesday, March the 21st. And you can come and stop by the observatory and meet the scientists and engineers. You can come and see how the telescopes work and bring your family, bring your friends. Open for 2 hours from 5:30 to 7:30 p.m. So that's in Galita. Make sure you come along to that. And then the second event to tell you about is part of the LCO's series of talks. We've got 2 speakers lined up so far. So one of them is in May, on May the 21st. So this is Gabriela Gonzalez, and she's actually was the spokesperson of LIGO, which is the experiment that detected gravitational waves. So she's a big deal. So she's giving a talk on May the 21st. So make sure if you're interested in gravitational waves, come along to that. And then later in the year, we've got a talk from Andrea Gaze on the supermassive black holes. So that's quite a long way away, so we're not sure of the location yet, but keep coming to Astronomy on Tap and keep listening in to hear when that talk will be. Okay, so we'll now take questions for Monica, if you guys are ready. Oh, sorry.
Do you want this one? Okay. Can you take the one from them? You take that one.
This one? Okay. Oh, right, the one in front of my face. Because it was like face on, you know.
thank you for sending all your questions in for Monica. So what should we start with? Okay, so a few people asked, how exactly are you tracking this space debris?
Well, it's a bit of a chicken and egg problem because I think you have to observe it first to track it, and so as you keep observing it, you update the coordinates and you can update the trajectory, and then you can get a more precise estimate. And once you have a very precise one, then you can it doesn't change much as it keeps going.
Okay, what about, I mean, it's obviously a big problem. A few people have asked, like, is there anything being done to remove it from our atmosphere?
Yeah, it is a big problem. As far as I know, there's no global solutions yet, but I think people are aware that this is definitely becoming an issue. They need to do something, but there's nothing that I know of as of yet.
And then sort of related to that, like if there's all this space debris out there, is there enough room to send more satellites into space?
For the small ones, they don't need a lot of room. They still keep a lot of space between them, but it's the same answer. Like, we are running out of room, and we're going to need to do something if we want to keep sending so many in the future.
There's another one I found. Okay, I had this question too. Are there any nice stories about animals that like survived going into space?
I think there were some dogs sent up after Laika, and they did come back.
There was I think there was some chimpanzees as well.
Yeah.
Yeah.
So it's not all bad. But
yeah, it was just like
the first one didn't go well. No.
Okay, on the removing space debris, do you know if any like technologies are being developed to actually do this?
I think they are. I don't know what they are specifically, but I think that future satellites will certainly be designed with ways to deorbit them in mind. Absolutely, yeah.
Okay, I had a few questions about this as well. Is there so much debris in the way that it's stopping humans from going out of the Earth's atmosphere? Is there too much debris in the way for us to escape Earth?
At the moment, no, I don't think so. I don't think that's one of the main issues. You have to be careful to plot your course to avoid the debris, but for now we can still go to Mars. We're going.
You actually have to be careful to plot your course. How do you, this is my question, like, how do you plot a course to avoid debris? There's a map of it everywhere.
There's the picture I showed was an actual NASA image of, they know where everything is all the time.
Okay. All right, I have a few silly questions as well.
All right.
Well, not silly, but interesting. Do you know about the spy satellites? Can you track them? How many are there?
I could tell you, but I'd have to kill you all.
Are there many Canadians in space?
That guy with the mustache who does the YouTube videos, like,
what's his name?
he's Canadian.
Chris Hadfield.
Yeah.
He did that. He sang
He sang that Space Odyssey.
the Space Odyssey in space. Yeah,
Yeah.
he's awesome. Okay. You want one more? Okay, this is a good question to answer. I think this will be our last question. Does this space debris contribute to global warming?
I don't believe they do.
Okay.
That's just us.
Okay. Well, we should probably still get rid of them somehow.
Yeah.
Okay. All right. Thank you very much, Monica.
Thanks.
All right. Stay here, Isabel. All right. We're now on to maybe the most exciting part of the evening, which is our raffle. I'm gonna get the prize.
Yeah.
Stretch.
Oh, okay. And I've been told, hot off the press, that Sputnik won our tip jar competition. I'm pretty glad about that. I think, sending an empty ball into space was pretty useful. Started a space race. A lot happened. Not so sure about the car.
Okay, make sure you've got your raffle tickets ready so we're going to draw out the numbers now. Remember, you win both a glass and a Women in NASA Lego set. Very exciting. Okay. Somebody's daughter wants that, apparently. Okay, do you want to pick out the first number? Okay, so Isabel has got number
040555. Anybody?
040555. Anyone? If you don't come up now, we will pull out another number, so make sure you check your tickets. Okay, don't think nobody is claiming this number. We're going to pick out another one. Okay.
040334. Nobody? Come on. You gotta come now or we're gonna pull out another number. 04.
We got someone.
We got somebody. Come on down.
Great. Let's just check. There we go. That's our first prize given out. Woo! Give him a round of applause. Okay, Monica, do you want to pick out the next number?
We'll dig inside. 040387. 040387. Oh, we got somebody.
Okay, we've got a winner. Oh, don't put it back. Oh, okay. You can say it.
Classic Neelay. Love you. You're the best. I love you.
Okay, we've got 2 more prizes to give out, so you can pick out another one.
040419.
We got a winner. Woo! Okay. Now, final winner.
040483. Anyone? 483. So I can take it? 04030. Oh, good thing I didn't read this number.
Okay. So just give a big hand to our speakers again, I think, before they leave the stage. You can do this.
Finally, just thank you very much to everyone for coming here. We hope you had as good a time as we did. Thank you, Matrix, for putting on this event. Thank you, everyone at LCO. And please come again next time, April 4th. April 4th. Bye, guys. Good night. And if you want to stick around, ask questions, everyone at Starpin should be able to answer your astronomy questions.